Welcome everyone. Today we are going to talk about the construction of single phase transform. Now, mm, let's say that to understand a transformer, we have to say that the basic diagram of a transformer is this laminated core, and this laminated core has a primary winding and a secondary winding. So the primary winding is, let's say, the supply voltage is applied to the primary winding, and due to the application of this primary voltage, there is a production of induced voltage in the primary coil, that is E1, right? And due to this E1, a flux, uh, let's talk about the flux linkage first. You have already seen in the video that I've posted earlier. Mm, So if there is a coil and a voltage is applied to that coil, then it will induce a flux which will act in this direction, which we can understand. The direction can be understood by uh, applying the right hand thumb rule. Now, here also there is a production of flux. Now, um, if there is an air gap, the dissipation of flux or the flux density will be much less. So we have provided a core, a laminated core around these coils so that the flux can travel through this laminated cores, right, to the next coil. Now, as the voltage induced in the next coil, the induced voltage will be E2, and which will again produce a output voltage of V2, right? So first of all, here you can see that the core of the transformer is made out of thin sheets. So these are not a cluster or a solid sheet, these are a cluster of sheets, which are also called laminations. These laminations are made out of high grade silicons. So the high grade silicons, what they do is provide lamination to the cores or core sheets. Now these laminations are provided uh, to reduce eddy current, and the silicon steel, which is provided as the core, is used to reduce the hysteresis loss. So there are two kinds of losses involved also. So one is the eddy current loss, another one is the hysteresis loss. Right? The laminations present in the transformer are insulated. So these are the laminations provided in the transformer. So these are also insulated with a heat resistance covering, or also known as enamel coating. This is also a kind of lamination, enamel coating. So this is also a kind of lamination to the core to make it heat resistant. So the types of these laminations are either L type or E type. laminations. So L-type and E-type are basically um, the structure of the mm, laminations. So if the lamination worked in two parts, so this is one part and another one is this part to cover the whole thing. So each section looks like an L. So these are called L-type laminations. And if the same thing happens in between the air gap also, so we don't need the air gap or the air gap must be minimum. So a lamination is being provided to the air gap too. So this kind of lamination is also provided in some cases. So this kind of lamination is actually E-type lamination, right? Now coming to the construction of transformer, uh, with the differentiation of core, transformers can be divided into two sections or two basic classified into two basic types. They are either core type or shell type. We'll talk about core type and shell type in the next slide. So let's talk about that. Now the figure that you see is actually a core type transformer, right? Now in the core type transformer, the magnetic circuit consists of two vertical lengths of limbs, right? This is the magnetic circuit shown by the arrow, right? Shown by this arrow. So this is the complete magnetic circuit, right? Now, mm, this magnetic circuit is consists of two vertical columns or legs or limbs and two horizontal columns called yokes, right? So this section is called a yoke. This section is also called a yoke, and these are limbs, right? Uh, to minimize the leakage flux, half of each winding Each winding, that means the primary winding and the secondary winding, the half of each winding is placed on each leg of the core. So the primary winding is present in the first leg as well as the second leg, and the secondary winding is present in the second leg as well as first leg. You can see that. Uh, you can see there is LV and HV, which is the high voltage and low voltage side. This is also the high voltage and low voltage side. So both the windings of both the section of high voltage and low voltage are placed in the limbs, right? The low voltage winding is placed next to the core. So every low voltage winding or the LV side, whichever that may be primary or secondary, is placed just beside mm, just beside this legs. These are adjacent to these legs. All the low voltage sides are adjacent to the legs, and all the high voltage sides are far away from the legs, right? Now, uh, so this mm, this type of construction is done to reduce the insulating material that is required by the machine to work, right? The the two windings are arranged in such concentric coils, uh, such that uh, it is also called a concentric cylindrical winding, right? So, so these are concentric cycles, right? And these are also concentric cycles, both having the primary and the secondary coils in their construction, right? Next, we come to the shell type transformer. Okay, now in the shell type transformer, both the primary and the secondary winding are wounded in the central limb. Now, what is the central limb? This portion is the central limb, right? So the primary coil and the secondary coil both are wounded around this central limb. And the low reluctance path, what is reluctance? You have seen, you have not done the chapter of magnetic circuits. Reluctance is actually resistance for magnetic circuits. So whichever pathway that resists the magnetic flux to flow is a reluctance path. So the reluctance of mm, a magnetic circuit is actually the resistance for a electrical circuit. In that way, it will be better for you to understand. Now, the low reluctance path is completed by the outer limbs, and each winding is subdivided into sections, that is low voltage section and high voltage section. So each the if these are the windings. So each winding is subdivided into two sections, which is the high voltage section and a low voltage section, and they are placed alternatively to form a sandwich. So if this is a high voltage section, this must be a low voltage section so that it forms a sandwich of two windings from the low voltage and the high voltage side, right? uh, this kind of windings are also called disk windings, right? And it produces a free pathway for the flux to flow. And the importance or the application or the advantage of a shell type transformer is it actually has a pathway for its own flux to flow, which consists of the low voltage flux as well as the high voltage flux. So there are two limbs. There are two limbs over which no coil is placed, and it gives a free pathway without production of any current through this mm, coil. So the lamination is here also is reduced by producing a free pathway for the flux to flow, right? If the flux flows through a pathway over which the coils are connected or coils are wounded, the coils would conduct some amount of current according to Faraday's law, right? So to reduce that current, we need lamination. So lamination materials are also reserved by this methodology. Now let's come to the ideal transformer. Now ideal transformer is nothing but the transformer without any losses, right? So this transformer has got no losses. So there is a particular direction of magnetic field or direction of phi m or the flux. So we have seen that earlier, that if this is the coil, so this is the coil which I am representing. This is the coil which I am representing, right? So if this is the coil, there is a certain direction of flow of magnetic field, right? So if we give this a pathway, so this is the pathway by which the flux will flow, phi m will flow, then this is the directional pathway for phi m to flow, right? So if the applied voltage is V1, we have talked about that. If the applied voltage is V1, there is an induced voltage, induced primary voltage, that is E1, right? And due to this induced primary voltage, uh, the flux will flow, and there will be an induced secondary voltage which is E2, and that is responsible for the supply of V2, right? V2 is the load voltage or the secondary side. Now, for an ideal transformer, some properties may be taken into consideration. The properties work for ideal transformer, but ideal transformer doesn't exist. There is always losses incurred in a transformer. So firstly, the primary and the secondary winding resistance are negligible. So there are no resistances in the primary and secondary windings, right? The core has indefinite permeability. Permeability is the allowance of magnetic flux through a particular material. That is conductivity in case of electric circuits, electrical circuits. For magnetic circuits, permeability is analogous to conductivity. Permeability so that negligible mmf is required to establish the flux in the core. Now secondly, its leakage flux and the leakage inductance are zero. So leakage flux and leakage inductance are the flux which weeps out from this magnetic core or the ferromagnetic core, right? uh, there are no losses to resistance, hysteresis, and eddy current. We have talked about this. So basically, this ideal transformer has no losses due to resistance, eddy current, and hysteresis losses. So the efficiency of this transformer is actually 100%. Now, let's talk about the phasor diagram of this. Now, let's represent this phasor V1, which is a supply voltage phasor, right? Now, this V1 is going to an inductor, right? So inductance will somehow deviate the magnetic field, right? So it will lag around 90 degree for an ideal transformer, right? Now the current due to that is I mu, which is the permeability current, or I1, right? So if this is the coil, so I1 is the permeability current which is equals to I mu, right? And phi m is the magnetic flux line that is being produced due to this current. Right now, the induced voltage in the primary side and as well as the secondary side, induced voltage and the secondary voltage. This is V2, this is E2, and this is E1. So these are all less than that of the primary voltage or the supplied voltage, right? So all the others are represented over in this axis, or the axis which is 180 degree apart to that of the primary voltage axis or the primary voltage phasor. Now, uh, for an ideal transformer, uh, this V1, this V1, and this E1 will be equal, right? And this E2 and this V2 will be equal. Similarly, um, the flux produced in the primary side will be equal to the flux produced to the secondary side, and the number of turns in the primary side must be equal to the number of turns in the secondary side. So if number of turns in the primary side is T1, right? Sorry, number of turns may not be equal in the primary and secondary, but they must be proportional to the voltage E1, and T2 must be proportional to the voltage E2, and simultaneously it will be proportional to V1 and V2, right? So from this phasor we come to a conclusion of a transformation ratio, uh, which is not only applicable to ideal transformers, it is also applicable to the non-ideal transformers too. So this is actually the transformation ratio, where A is represented as the transformation ratio, that T1 is the number of turns in the primary side, T2 is the number of turns in the secondary side. E1 is the supplied induced voltage in the primary and induced voltage in the secondary E2. P1 is the supplied voltage in the primary, V2 is the supplied voltage in the secondary, and I2 is the supplied voltage in the secondary or induced current in the secondary, um, and I1 is the induced current in the primary. So here you can see that the current is actually inversely proportional to the number of turns, the induced voltage, and the primary voltage of primary or secondary voltage of the transformer, right? So from these uh, transformation ratio, so these are the different transformation ratios of an transformer, we can come to a conclusion that these equations can be formed which are not only applicable to the ideal transformer, these are applicable for non-ideal transformers too. So if any of these quantities needed to be found and all the other three quantities are given in sum, then we can easily find the fourth quantity, right? Now here is the power equation for the induced voltage. So if there is an induced voltage, if there is an induced current, there must be an induced power, right? So these are the this is the equation for induced power, and this is the equation for the input and the output power. Okay, so input and output power must be same in case of ideal transformers, but may vary. Uh, this may vary if the losses are included in the calculation of a transformer, right? So that's it for today. It's a pretty long lecture, so hope you'll see it, and we'll continue with the next class, right?